started. So today, class N, talking about graphing polynomial functions and even and odd functions. And actually, before we kind of look at any of this, we should probably write something up here on the top because this page I feel like is missing something important, which is what is a polynomial? So here's what a polynomial is. A polynomial is a function, usually of x, but any variable is fine, where all the powers or exponents of the variable are non-negative integer numbers. That's what a polynomial is. So all the things on this page are examples of polynomials. F of x equal to x, x is raised to the first power. F of x equal to 2x minus 3, x is raised to the first power. F of x equal to x squared, second power. F of x equal to 2x squared plus x plus 3, second power. Or second degree, first power, 0th power. So all of these functions, the powers of x are all or I should say non-negative integer powers. And I just say non-negative because 0 is a totally valid power of x as well. We just usually write x to the 0. So you could totally think of this second one if you really wanted to, although no one is going to do this, but you could think of this one as f of x equal to 2x minus 3 times x to the 0th power. But no one's writing it that way. So you shouldn't write that. But I just want to point out that the 0th power is a valid power to show up for a polynomial. So all these things are polynomials. Some examples of things that are not polynomials that we've talked about. I can give you 2 examples right off the bat of some not polynomials. So here are some not polynomials over here. I'll give you 2 examples of things we have talked about. F of x. Let me do this real quick. F of x equal to the square root of x. What's the power on that function, on that x? 1/2, which is not an integer, right? 1/2 is not a whole number. And another example, the function that we have briefly talked about that is not a polynomial is 1 over x, which can be rewritten as x to the -1. That is an integer number, but it's a negative integer number, so that's not a polynomial either. So any of these things that have powers of x where you have not integers or not positive powers, those are not polynomials. Okay. So all these things here are polynomials, and we have a few things to talk about. So typically a line is a polynomial of degree 1. You can also call it a linear function. We've talked about lines quite a bit. Y equals mx plus b. So you've got like y equals x or y equals 2x minus 3, or really, I should say almost, there's one exception here, almost any line we've talked about is a polynomial of degree 1 because you have an x to the first power. Can any of you think of a line that might not have an x to the first power? Good question. Something like this. Maybe it's horizontal. Like if what about the line y equals 5? Is that a line? A line. Is there an x there? I mean, you could say there is. You could say there's an x to the 0th power if you really wanted to be pedantic about it. But no, there's not an x there. So most lines are linear functions or functions of x to the first power. But horizontal lines are actually 0-degree polynomials. So that's something else we should mention over here. Sorry, I know I'm like writing all these things kind of on the side here. So here's some not polynomials here. And then I will just point out that a 0-degree polynomial, although not exciting, does count. A 0-degree polynomial could be something like f of x equal to 5 or y equal to -7. Those are some examples of 0-degree polynomials. And they are also lines that are specifically horizontal lines. Okay. So both of these functions here have x to the first as the highest power of x. I should also point out that the word degree just means whatever the highest power of x in the polynomial is. So this next section, parabolas, the graph of a polynomial degree 2. We can also call this a quadratic function. This table is too low. Here are some examples. F of x equal to x squared, f of x equal to 2x squared plus x to the first plus 3. Or even this one written kind of in a different way, f of x equal to x minus 2 squared plus 3. So even though it's not immediately obvious, if you multiplied this out, you would have x squared minus 4x plus 4 plus 3. And then the highest power of x would be x to the second. So it would be a degree 2 polynomial. And it would be a polynomial because all the powers of x are, again, non-negative integers. Okay. And thirdly, cubic function is a polynomial of degree 3. We don't really have a good name for its graph. So here are some examples. Again, we're just looking at things where you've got powers of x that are not negative and not fractions, right? Integers. I shouldn't say not fractions because there's lots of not fractions that are also not integers like square roots. But here we have something like x cubed plus 2x squared minus x plus 4, or x minus 2 cubed plus 3, or even x minus 2 squared times x plus 1. So all of these last two in particular, if you multiplied them out, you would get x cubed plus something times x squared plus something times x plus some constant. This one too, if you multiply this out, you have something x cubed plus something times x squared plus something times x plus a constant. So the degree of the polynomial is really the highest value of x you would see if we multiplied it all out and wrote it in kind of the standard way, which is highest power of x, then the next highest power of x, and so on and so on. And so on. I should also mention, even if you write it in a not standard way, the degree is still the highest power of x. So for example, if I wrote out y equal to 2 minus x to the first plus 5x squared minus 7x cubed, that's still a degree 3 polynomial because the highest power of x is still 3. I wouldn't write it that way. I would definitely rewrite it as in the standard negative 7x cubed plus 5x squared minus x to the first plus 2. But either way you write it, it still has the same highest power, so it still has the same degree. All right, I should do this for you guys. If I'm not missing anything here. Typically, when we start graphing polynomials, it is going to be easiest to graph them usually if they are factored already, or if we factor them. That really kind of depends. I'll say it's usually easier to see the x-intercepts if they're already factored. It's usually easier to see the y-intercept if it's not already factored, but we'll talk about it. Before we can really get into graphing them, there's kind of one more thing we need to know, is how the end behavior of polynomials works. So we have this little table here where we're going to talk about things that can happen. And here I'm going to talk about the examples I keep in my mind when I do this. So you can have a degree of a polynomial either have a highest power that's even or a highest power that's odd. Those are the only choices, right? If all the powers are integers, the highest power is either an even or an odd number. It could be 3, or it could be 2, or it could be 4, or it could be 7, right? It could be any integer number. So if it's even and the leading coefficient is positive, I would encourage you all to think of the graph y equal to x squared. That is a polynomial with even degree with a positive leading coefficient. And I know it looks like this. And just for contrast, if I was doing a polynomial with even degree with a negative coefficient, I'm going to think of y equal to negative x squared, which looks the same, except it's been flipped over or reflected vertically. So it's going to be opening downward. So here's the idea. Any even degree polynomial whose leading coefficient is positive, meaning the coefficient of the highest power term is positive, we're always going to have this behavior where on the left it's going up and on the right it's also going up. Then maybe some weird stuff happens in the middle, you find a bunch of intercepts or whatever, but the end behavior is it's going to be up on the left, up on the right. Yeah. Sorry, where's that? Oh, or a quadratic function. Yeah. Sorry, I know. Thank you for asking. So some people like to say, I just like to draw these little arrows. Some people like to write it starts high and ends high. Or some people like to say it starts in quadrant 2 and ends in quadrant 1. So you could say starts high in quadrant 2 and it ends also high in quadrant 1. Just to make sure everyone's cool with the quadrant stuff, the coordinate axis system, we typically divide up into 4 quadrants. The first quadrant being where everything's positive, and then we just go counterclockwise. So there's quadrant 2, there's quadrant 3, there's quadrant 4. So it totally works if you think about y equals x squared. Y equals x squared starts high in quadrant 2, and then does whatever the graph does, and then ends high in quadrant 1. And similarly for y equal to negative x squared, it's going to start low and end low. So we're going to start low in quadrant 3. And we're going to end low in quadrant 4, sorry. What I remember about even degree polynomials is they always do the same thing on both ends. It starts high, it ends high, it starts low, it ends low. So even polynomials kind of have the same thing happening, whereas odd polynomials or odd degree polynomials have the opposite thing happening. Meaning if you start high, you're going to end low, or vice versa. If you start low, you're going to end high. So for odd polynomials, I'm going to think of my least favorite polynomials to draw, y equals x cubed, which I know looks kind of like this. So I'm starting low and ending high. So it's going to be down on the left, up on the right. Whichever, and again, if I was a student, I would just draw little arrows like that and not write all the other stuff. But you can write, but some people like the other stuff. This one's going to start low. Starting low, we're starting on the left, so we're starting low in quadrant 3. And we're going to end high on the right. So we're going to end in quadrant 1. And finally, the opposite of that, the vertical reflection of that, y equal to negative x cubed, looks like that. And it's doing the opposite thing. Instead of starting low and ending high, it's starting high and ending low. So we start high in quadrant 2, and we end low in quadrant 4. So I know I've picked a few examples because they're easy for me to remember, but this is true for any polynomials that meet these criteria. So for example, this polynomial right here, y equal to x cubed plus 2x squared minus x plus 4, it has an odd degree because its highest power is an odd number, and it has a positive leading coefficient because the coefficient of x cubed is 1, positive 1. And so this one would start low and end high. And maybe some of this stuff's going to happen in the middle, but as far as the end behavior is concerned, it's starting low and ending high. Or it's starting, I always say it goes from down to up. That's whereas something like, no, I don't have any examples there. So I should point out, no, I shouldn't. I should say, let's do some examples. Also, if you have any questions, don't hesitate to ask them. So the next pages have like this whole kind of what's what I'm looking for, template for graphing polynomials. You do not have to do all of these things every time you graph a polynomial. In fact, we'll do an example at the end where we kind of do it a little more bare bones, but this template is available on Canvas if you want to print it out and use it. It's totally fine, but you don't have to. So this is already factored for us. It's probably going to be useful to multiply it out since it's relatively easy to multiply out. So I could multiply this out and write it as 3x squared minus x cubed. All right. Well, in fact, I should point out this is not written in the standard way. Right? Usually we write the highest powers first. So writing the highest powers first, this is going to be negative x cubed plus 3x squared. Okay, so in some way, shape, or form, we should make note of all these things or think about them. The degree is 3, the highest power of x I got. Now, again, I want everyone to see if you don't multiply it out, the degree is still 3. So you have to think about, if you're not going to multiply it out, what the highest power would be if you did multiply it out. Okay, leading coefficient is negative. So by that 2 pieces of information, we know it's odd, so we're doing the opposite thing, and we know it's negative leading coefficient. We're starting high, we're ending low. We're starting in Q, 2? Yeah, right. That's quadrant 2. We're ending over here in quadrant 4. So starting in quadrant 2, ending in quadrant 4. Or honestly, what I would really write is, I know I'm going to be like this, high then low. That's the way I like it. Starting high, ending low. So I'm gonna start up here, do some stuff. Let's find the y-intercepts. The y-intercepts are usually pretty easy to find. If we plug in 0 for x, f of 0 is going to be, now, I really don't need to multiply this one out to do it, because if I plug in 0 here, 0 squared is 0, and 0 times anything is 0. So typically, a lot of the time, if one of your factors is x or x to a power, the whole thing's just going to be 0 for the y-intercept. So f of 0 is 0 squared times 3 minus 0, which is 0 times 3, which is 0. You don't need to show that much work. Once you see 0 as a factor, end of story. You know that it's equal to 0. On the other hand, the x-intercepts are usually a little bit more work. So we're going to set y equal to 0 and solve for x. So we set either factor equal to 0, and we end up getting x squared equal to 0, which becomes x equal to 0. And then we end up getting x minus 3 equal to 0, which becomes x equal to 3. And then we're going to talk about something which we haven't talked about before, which is the multiplicity of each intercept. So the multiplicity of each intercept just it actually kind of refers to the degree of each factor that each intercept came from. So this x minus 3 factor, what's the power on that factor that I haven't written? Right. And this x factor, the power on that factor is the second power. So this solution, x equals 0, came from setting this factor raised to an even power of 2 equal to 0. So what I would say is this x equals 0 has what's called a multiplicity of 2. Similarly, contrastingly, x equals 3 came from the x minus 3 to the first power, and it has a multiplicity of 1. And we're going to skip the classifying part for just a second, because I think it's easier to see if we do the part after that. Again, I don't think this number line part is necessary, except to show you what I want you to actually see. So on the number line, we're going to put all of the x-intercepts. In this case, 0 and 3. And the reason we're doing this is because the x-intercepts are where the function can change from being positive to negative or negative to positive. Because you have to go through 0 if you're going to go from positive to negative or negative to positive. Okay, that's not entirely 100% true, but it's true for polynomials. We're going to see if we graph rational functions. There's another thing we have to talk about. But for polynomials, always true. If you want to go from positive to negative or negative to positive, you have to go through 0. So I'm going to check and see over here. Is my function positive or negative? I'm just going to pick any number I want that is bigger than 3. 4 is the boring choice. You pick 4,000. Any number bigger than 3 is totally fine. If we pick 4, though, and you plug it into the original function, 4 squared is positive, 3 minus 4 is negative. So the whole thing over there is negative. And it doesn't matter if you pick 4 or 4,000. 4,000 squared is also positive, and 3 minus 4,000 is also negative. Because any number bigger than 3, squaring it will be positive, and 3 minus it will be negative. So you're always going to get a positive and a negative if you pick something bigger than 3. Picking something between 0 and 3, like 1. 1 squared is positive, 3 minus 1 is positive, so the whole thing is positive. And that would be true no matter what number between 1 and 3. We can't pick 1, or sorry, we can't pick, between 0 and 3. We can't pick 0, because plugging in 0 will get you just back 0, and that's until it's positive or negative. And we can't pick 3 for the same reason. You have to pick something specifically between the numbers. Lastly, picking something less than 0, like -2. -2 squared is positive. 3 minus -2 is also positive, because it's 3 plus 2, which is 5. So that's a positive times a positive, which is positive. So what's going to happen is our graph is going to be above the y-axis over here, above the y-axis over here, and below the y-axis over here. So it might look something like this. I'm not really going to, well, I'm going to kind of graph it. It's going to do that. It's going to hit the x-intercept, and then it's going to hit this x-intercept, and then it's going to do that. Positive, positive, negative. So here's what I wanted to really say. I don't always do this because I don't like to. But what I want to say is we can classify the x-intercepts. We can see that at 0 is the graph bouncing off the x-axis or crossing through the x-axis? It's bouncing. How about at 3? Are we bouncing off the x-axis or are we crossing through the x-axis? Crossing. So what's happening here is at x equals 0, which had a multiplicity of 2, we're going to bounce. And at x equals 3, we're going to cross. And what we're always going to see is that for intercepts with even multiplicities, they always bounce. For intercepts with odd multiplicities, they always cross. So you always get a bounce when you had an even multiplicity. You always get a cross when you had an odd multiplicity. And it's really because when you have an even power, something to an even power, whether you plug in a negative or a positive, raising it to an even power spits out something positive. Whereas if you had an odd power, plugging in something positive gets you back a positive, plugging in something negative changes the sign and gets you back a negative. So that's really why the odd powers allow you to change signs and go from positive to negative, meaning you cross, whereas the even powers don't allow you to change signs, meaning you go from positive to positive or negative to negative and you bounce. So we pretty much got, well, we definitely got everything we need, and I've kind of already drawn the graph, but let's actually draw the graph correctly. So I'm not going to plot too many points. In fact, I'm going to plot the bare minimum of points I can get away with. I'm going to plot 0, and I'm not even going to plot 3 until I graph the thing because I'd rather not mess it up. So I'm going to say, okay, I know I'm going up on the left, down on the right. So I'm up over here, down over here, and I'm going to bounce here. I'm going to cross at 3. So I'm going to draw it like this. Now, if you're going to bounce specifically, although with them, you should prepare. Like you don't want to come at this thing too jagged and then have to like bounce off in a jagged sort of way. Polynomials should always be smooth, right? There's no pointy points. There's no jagged end, anything. This nice smooth curve. It gradually comes down there. It just touches it and then bounces off. And then it turns around and has to cross at 3. So then I will plot that point there. I knew it was going to be there, but I wanted to kind of give myself room to draw it nicely. So that point's 3, 0, that point's 0, 0. And that's all we can really do. We can find the intercepts, we can find the end behavior, and that's kind of it. I will point out, we cannot find this turnaround point right here. I don't know what point that is. That's what we're going to learn how to do in calculus. Find that point right there where it turns around. That's not for us, that's for later. It's kind of like finding the maximum by finding the vertex of a parabola, but more complicated. All right. Anything else I want to say about that before we move on to the next one? Check my notes. I think there was something I wanted to say that just popped into my head. I guess not. Fine. We got other things to graph. Let's move on. So this next one is a bit more complicated. X times x plus 2 times x minus 4 squared. Yeesh, all right. So I'm going to ask all of you to think about it for a second. And when you're ready, either type in the chat or show me on your fingers what the degree of this polynomial is. You can keep your hand. Yeah, that's it. All right, yeah. Cool. I see mostly right answers. I think I see a few that are missing 1 power of x. So the degree is gonna. How about in the chat? Anyone in the chat wanna? You can write me a private chat. You guys are like, we're not even paying for that. Okay, so it is degree 4. Because if you multiply the whole thing out, you'd have x times x minus 4 times another x minus 4, which would give you an x times x times x times x, which is x to the 4th. Another way you could attack it, if you don't want to do that exactly, is you could say that's an x to the 1st, that's an x plus 2 to the 1st, and if you add up all those powers, 1 plus 1 plus 2 is 4, which is what the degree is going to be. Always works. It also works by adding up all the multiplicities, which is kind of the same thing. So the degree is definitely 4. The leading coefficients. I really don't want to multiply this thing out. Like I'm trying so hard not to multiply this out because it's a pain. But I do want to think about what the leading coefficient would be. So if I multiply this out, x times x plus 2 would give me an x squared plus some other stuff. X minus 4 times x minus 4 would give me x squared plus some other stuff. And then the x squared times the x squared would give me a positive x to the 4th. So my leading coefficient is positive. Looking back for just 1 second at the previous one, if we hadn't actually multiplied this out, but just thought about multiplying it out, you can see that the x squared times the minus x will give you an x cubed, but it would have a negative leading coefficient because it's an x squared times a negative x. So you can usually get away without actually multiplying the whole thing out, but you have to be careful. You can also multiply it out. It just sometimes it's really, really gross. Why? Yeah, oh, and behavior. So let's see, degrees even, meaning they're both going the same way. They're either both up or both down. And the leading coefficient is positive, meaning they're both going to be up. So we're going to go up, up. Or I guess if you want to say words about quadrants, we're starting up in quadrant 2. And we're ending in quadrant 1. So we're going to start over here. We're going to end over here. Some stuff's going to happen in the middle. Y-intercepts, again, we're going to get y equal to 0 as our intercept, because if we set x equal to 0, f of 0 is 0 times, I should really just stop there. 0 times a bunch of other stuff is still 0. I could write it out. 0 times 0 plus 2 times 0 minus 4 squared. But don't trick yourself here. I've seen way too many people do this and say that the answer is 2 times 16, which is 32. Not. It's 0 times 2 times 16, which is 0 times 32, which is 0. So make sure that when one of the things you're multiplying is 0, the whole thing is just going to be 0. All right, x-intercepts. So we're just going to set the whole thing, x times x plus 2 times x minus 4 squared equal to 0. And really, we're just setting each factor equal to 0. So we're setting x equal to 0 and getting x equal to 0. That's kind of boring. We're setting x plus 2 equal to 0 and getting x equal to negative 2. And we're setting, kind of ran out of room to write arrows here, x minus 4 squared equal to 0. You can think of taking the square root of both sides here, but you really don't have to. If something squared is equal to 0, what's the only number we can square and still get 0? 0. The only number squared that's equal to 0 is 0 squared. So you can say, well, the insides have to equal 0. There's no other option. If x minus 4 equals 0, we get x equal to 4. Okay, x equal to 0. What's the multiplicity on that one? Or, in other words, what's the power on that factor? 1. And how about for x equal to negative 2? What's the power on that factor that it came from? Also 1. And for a change of pace, for x equal to 4, what's the power or the multiplicity that was on that factor? Yeah. So the odd multiplicities are going to cross, the even multiplicities are going to bounce. So we know that we're going to, at x equals 0 cross, at x equals negative 2 cross, and at x equal to positive 4 bounce. Which to me kind of negates the need to do anything with the number line at all. I guess that's not, no, that's pretty true. So I would say, in my opinion, you can skip the whole number line thing and just go to the graph. So I'm going to go to my graph and I'm going to plot my intercepts. Really, my intercepts are really the only points I've got to plot. So my intercepts are 0, negative 2, and 4. So there's negative 2, 0, 1, 2, 3, 4. I don't think we really need to draw those little things, but I did it, so oh well. And then we know that we are up on the left and we are up on the right. So we start up here, and you should draw, I think, from left to right. We start up here, and then we're going to plan. We know that we're going to bounce at 4 and cross at the other 2. So we're going to come here, we're going to cross, cross, bounce. Cross. And then you have to turn around. Oh, I know I was going to say from the previous one. Cross. And then don't cross, right? You can, so if you come at this too sharp, it's going to be hard to draw. So kind of make it gradual, give yourself room to turn around and then bounce off like that. And if you've got your crosses and your bounces correct, the end behavior should also be right. And I remember what I was going to say before, which is that the degree of the polynomial, 1 less than that is the most number of turnaround points you can have. So not that it's always true, but here the maximum number of turns is 3 minus 1 equal to 2. And we have exactly 2 turns. One right there where we went from going this way to going that way, and one right there went from going that way to going that way. Or changes in direction if you prefer. Same deal here, right? The maximum number of turns should be 3. And we have exactly 3. We have 1, 2, 3 places where we turn or change directions. And I should say, just because the maximum number of turns is some number doesn't mean you're always going to get that many. You could say that the maximum number of turns was like 7, but only get 3. So it's just saying there's an upper limit, but you don't actually always get that many. Not something you have to think about really, but it's just good to know that you can only turn so many times. If you try and draw too many turns, it won't work out. What I would say is don't draw any, like I could have drawn this kind of, like if I was trying to make it look funny, I could have drawn like a bunch of turns here, but like that's not really allowed because my maximum number of turns is 3. So don't throw in any unnecessary turns. What I would say. Let's see. Let's look at this next one. The next one's a good example of unnecessary turns, or not unnecessary turns, but having more potential turns than we actually have. It's really light. Okay, that's fine. I guess we'll work. So this one doesn't have all the hoopla about like all the, oh gosh, template. It doesn't have the template, which is fine. We don't need the template to do all this work. We just have to think about the things we need. So first, I'm going to think about the degree and the leading coefficient. That's going to tell me the end behavior. So let's see. My degree is 6. 3 plus 1 plus 2. Or if you think about multiplying this out, x cubed times x times, I'm going to get an x squared there. And x cubed times x to the first times x squared is x to the third plus 1 plus 2, which is x to the 6th. So the degree is 6. Oh, I know what I want to say. The degree is also what you get if you add up all the multiplicities. In the previous one, the multiplicity was 1 plus 1 plus 2, which is 4, which was the degree. That's also another way to think about it. All right, so when looking at the leading coefficient, I typically ask myself, do any of the x's have a negative sign in front of them? No, great, it's positive. If any of them have a negative sign, then you have to think some more, because it could be positive or negative. Let's see. The leading coefficient here is definitely positive. So just like before, where I had an even degree and a positive leading coefficient, that means we are both up on the left, up on the right. We're starting in Q2, ending in Q1. So we are up and up. Okay. Y-intercept, all these are 0. I'm gonna have to give you guys a different one before we're done here. So y-intercept here is also going to be 0, which is not very exciting. But if we set x equal to 0, we get y equal to 0 times a bunch of other stuff is just 0. I really, really, really want you to see that. Don't do all the multiplying out to be like, oh, I got 0 times other things. 0, done. X-intercepts, always a little more work. But we're fortunate here, bless you, is that, bless you again, the whole thing is factored for us. So if we just set the whole thing equal to 0, as long as it's already factored, our job is simply just to set each factor equal to 0. So we're going to say, okay, well, we're going to get x cubed equal to 0, or x minus 1 equal to 0, or x minus 3 squared equal to 0. And each of these are just going to result in essentially setting x, or the insides of your factor, which in this case is just x equal to 0. This is going to give me x equal to 0. This is going to give me x equal to 1. This is going to give me x equal to 3. For x equal to 0, the multiplicity is 3. For x equal to 1, the multiplicity is 1. For x equal to 3, the multiplicity is 2. Okay, let's do a check. What do those multiplicities add up to? Right, 6. The degree, as they should. So if you're checking multiplicities, they should add up to your degree, and vice versa. If you're checking degree, it should add up to what your multiplicities add up to. So it's a good check. All right, so we know that for the multiplicity 3, we're going to cross because it's odd. Multiplicity 1, we're going to cross because it's odd. Multiplicity 2, we're going to bounce because it's even. I'm trying to think of a good way to remember that. all I can think of is even has the letter E and bounce has the letter E and cross has the letter O and odd has the letter O. That's not great because bounce also has the letter O, but it kind of works. Okay, so I think that's all we really need. So let's do the thing. We're going to plot our x-intercepts. We would also plot the y-intercept if we had one that wasn't the origin, but so far all of our examples are. And we might have enough time to get to one, but we might not. It's just still something else we have to talk about. So x equals 1. Now, what I would say is your graphs don't have to be perfectly, what's the word I'm looking for, to scale. You don't have to have your 1 and your 3 exactly spaced perfectly. You don't have to make them really small. I would give myself room to work with here. So I'm going to make 1 here and 3 there. And I'm not really going to care about anything else. I guess I can make 2 there. Okay, fine. But give yourself enough room so you can actually draw the thing without having too much trouble. And again, the y part doesn't have to be the scale either. I'm probably making my y's not nearly large enough. Totally fine. I'm just going for the general shape. We're starting up on the left, and we know we're going to cross, bounce again, just like last time. So we're crossing, we're bouncing, and behavior check. So this is the general way we graph polynomials. We find the intercepts, and we just kind of figure out whether it's bouncing or crossing at the intercept. Later on, when you take calculus, you'll learn about kind of a different way of finding these relative minima and maxima, which we can't do at this point, but also using that information to help you graph it in a slightly more precise way. For now, this is what we've got, which is fine. The idea here is just to kind of know what the shapes of these things look like so that we have a good idea of how they look. All right, the other thing we want to talk about, which uses some of the same words, but in a very different way, is what an even function and an odd function are. So when I think even function, my number one example in my brain is y equals x squared. Y equals x squared is a good example of a lot of things. It's just like you should know that one. It's everyone's favorite. And it's an even function because it has symmetry about the y-axis. If you reflected it horizontally, it would still look the same. That is the hallmark of being an even function. Is that if you split it down the y-axis, the right side and the left side would be like mirror images of each other, or as I prefer to say, if you reflect it around the y-axis, it doesn't change how it looks. So the way we actually find that is by setting f of negative x equal to f of x and showing that they're the same, or I should say, by showing that f of negative x equal to f of x. So just for example, let me grab one thing here. Apologies. I'll make sure I'm the same. Oh yeah, as an example. So for example, f of x equal to x squared. What's f of negative x? Well, it's negative x quantity squared, which is negative x times negative x, which is positive x squared. Oh, look, those are the same. So that's what it means when you're trying to show that these are equal to each other. You're just subbing in negative x or x and then doing whatever multiplication to show that they're equal to each other. It definitely counts 110%. I mean, not really 100%. Okay, don't be wild. Yeah, it has the right shape. It has the look. If you flip the absolute value function across the vertical axis, it's still going to look the same. It's an even function. It's a great example. Other functions that we haven't talked about yet, cosine of x is also an even function. It's kind of the number one trig example of an even function. An odd function, on the other hand, has symmetry about the origin, also called rotational symmetry. My favorite example, the polynomial, is y equal to x cubed, even though I don't draw it very well. And the idea is that if you take y equals x cubed and you rotate it 180 degrees about the origin, it's going to look like it did originally. The other way you can say this, which I like less, but also works, is you can reflect it both horizontally and vertically. And if you do both of those reflections, it'll look the same as it did originally. I guess I could draw it. Here's y equals x squared. You can flip it vertically, or not flip it vertically, flip it across the vertical axis. It's going to look the same. Whereas x cubed If you rotated it 180 degrees, it would look the same. Or if you did a vertical flip and a horizontal flip, it would look the same. I should point out, because it is true, that when I write f of negative x, when I do the negative on the inside of a function, that's like doing a horizontal reflection. So we are literally writing here that the horizontal reflection is the same as the original function, which is what we have just said it should be graphically. What we're saying here is actually the horizontal reflection is the same as the vertical reflection, which should also be true, right? If you did the horizontal reflection, so let me just show you, I guess I can show you the picture. Here's your horizontal reflection, f of negative x. Here's your vertical reflection. Take that, flip it over. Oh, look, if you can draw, they look the same. F of negative x and negative f of x are the same. It's a odd function. It's an odd function. The way you would show that, though, is to show that, I'm kind of running a room here. So if our function is x cubed, f of negative x is negative x quantity cubed, and a negative x times a negative x times a negative x is a negative x cubed, versus negative f of x is just negative x cubed. Oh, look, once again, these are the same. So showing those are the same is how you show a function is odd. Something to be aware of that's totally 100% true for these problems. If you have negative x parentheses raised to an even power, you're going to get rid of the negative. Because it's a negative times a negative times a negative times a negative an even number of times, so you're going to get a positive. If you have a negative x raised to an odd power, you're going to retain the negative sign. It's going to stick around. So let's look at some examples. We already did f of x equal to x squared, so let's skip that one. Let's show that this function is an even function. Now you might notice that in this function, showing it's even, all the powers are even. That's not a coincidence. So to show that g of x is even, we are going to show that g of negative x is equal to g of x. And whenever you're showing a function is odd or even, or neither, because neither is an option as well, neither is what most functions are, you're going to start with that function evaluated at negative x. So start with g of negative x. And literally just take your function g of x and plop in a negative x for every x. So I have 2 times negative x to the 6th minus 3 times negative x to the 4th plus 1. I will point out, just because it's worth pointing out, this is a polynomial where all the powers of x are even. X to the 6th is even, x to the 4th is even, and the power here on x, which is x to the 0th, is 0 an even number? Definitely is. You're not sure about that? Think about what it means to be an even number. It means we're divisible by 2. 0 is definitely divisible by 2. You can also think about it as every other number is even and every other number is odd. So if 3 is odd and 2 is even and 1 is odd, then 0 better be even. So here we end up getting, well, negative x to the 6th is negative x, right? It's negative x times itself 6 times, which is going to be 2 times positive x to the 6th minus 3 times positive x to the 4th plus 1. Oh, that's definitely the function I started with. Check. That means it's an even function. So g of x is indeed even. Now I'll point out, I just said that this thing that had all even powers was an even function. Now what I really should have said more specifically was any polynomial with all even powers is an even function. And similarly, although we don't have an example of it, any polynomial with all odd powers is going to be an odd function. But this thing here, g of x equal to x to the 5th times square root of x to the 4th plus 9, is not a polynomial. There's a square root in there. That makes it automatically disqualified from being a polynomial. So to show it's odd, we're going to show that g of negative x is equal to negative g of x. And there's a couple different ways people like to do this. I'm going to show you the way I think is the easiest, but you might disagree. So I'm going to start with g of negative x, like I always do, no matter what I'm trying to show when I'm talking about even, odd, or neither. So g of negative x, I'm just going to sub in the negative x. I'm going to get negative x to the 5th power times the square root of negative x to the 4th plus 9. And then Negative x to an odd power is negative x times negative x times negative x times negative x times negative x, which is going to end up being a negative overall. Because I have a negative number multiplied by itself an odd number of times. So that's going to be a negative x to the fifth times the square root of, well, negative x to the fourth is positive x to the fourth. That's 9. Some people then just like to factor out a -1 and say this is equal to -1 times the remaining stuff, and that is equal to, right, -1 times x to the fifth times the square root of x to the fourth plus 9, which is equal to -1 times g of x. Or, and I think I've seen students generally prefer doing it the second way, or people say, I've got this, and then I'm going to just see what negative g of x is as well. Well, negative g of x is just negative in front of your whole function. And there is no distributing to do here. We only distribute across addition or subtraction, but this is negative x to the fifth times the square root of x to the fourth plus 9. So we don't distribute the minus. But they are the same. That and that, totally the same. So we definitely have an odd function. So g of x is odd. Not strange, it just has rotational symmetry. So if you were to graph this, which might be worth doing if you have a moment to look at Desmos, you will see that it looks the same on the right as on the left, except the right side is flipped over compared to the left side. Okay, a couple more slightly more complicated ones. So typically, if someone is asking you about evenness or oddness or neitherness, typically it's going to be phrased as, I'm not going to tell you to show me it's even. I'm going to ask you to find out whether it's even or whether it's odd or whether it's even. So here is the process for doing that. You always check for even first, not even, then you check for odd. If it's not odd, then you're done, you say it's neither. So the process is 1, check if it's even. So we're going to check to see what f of negative x is. And if it's equal to the original thing, then we're done. It's even. So f of negative x is negative x quantity squared plus 1 over 2 times negative x to the 7th minus negative x to the 3rd. And then we should do a little bit of simplifying. Negative x quantity squared is just x squared plus 1. But the bottom is going to be negative 2x to the 7th minus x cubed is plus x cubed. And then we have to ask ourselves, does this look exactly like the thing we started with, or can we simplify it so it did? And the answer is no, it doesn't look exactly the same. The top is still the same, but the bottom is decidedly different. So this, we ask ourselves, does this equal f of x? And the answer is a resounding no. So it's not even because it failed for f of negative x to be f of equal to x. So it's not even. So then we continue on and we check the next thing. Well, could it be odd? So if that fails, check if it's odd. Okay, so now we already have f of negative x. Let's look at negative f of x. So negative f of x is equal to -1 times x squared plus 1 over 2x to the 7th minus x cubed. Now here's where especially with fractions, you have to be kind of super careful. You multiply that -1 by the fraction, it doesn't multiply by the top and by the bottom. If you did that, you multiply by -1 over -1, which is just 1, which is not the same as -1. So we can decide whether we want to write this as -1 over 1 times the fraction x squared plus 1 over 2x to the 7th minus x to the 3rd, which is probably not what I want to do because I'm trying to get something that looks like that, and I'm going to get kind of the wrong thing. Or I can think of -1 as the fraction 1 over -1. That's also a valid thing to do. What's 1 divided by -1? -1. And if we do it that way, and we multiply these fractions, we get top times top, bottom times bottom. That's going to be, well, the top 1 times anything is just what you've got. And -1 times all this stuff, we do distribute, and we get -2x to the 7th plus x cubed. And oh, that checks out. That is the same as that. That is equal to f of negative x. So it is odd. But if it wasn't, we would say it's neither. So this last one here, we would do the same thing. So we look at f of negative x. It's 2 times negative x to the fifth plus 3 times negative x squared plus 1. And if we multiply this out, that's negative 2x to the fifth plus 3x squared plus 1. And that's definitely not the same as the original function. And then we ask ourselves, okay, what about negative f of x? Well, negative f of x is negative 2x to the fifth plus 3x squared plus 1. If we distribute the minus sign, that's negative 2x to the fifth minus 3x squared minus 1. But that's not equal to negative or f of negative x. Right, that's not the same as that right there. So f of negative x didn't equal f of x, and f of negative x didn't equal negative f of x. So since we weren't even and we weren't odd, this function is neither. You can just say neither, or you can say neither odd nor even. So that's how you show if a function is even or odd or neither. Check to see if f of negative x equals f of x. If not, you check to see if f of negative x equals negative f of x, and if that's not, then no, it's neither. All right, that's all I have got. Thanks for hanging in there for an extra minute.